Hi everyone, my name is Mason. I had the student 4 file for the first wiki assignment. So for the first questions, first couple questions, it says complete the following. So here I have this structure. It is a nucleophilic aromatic substitution reaction because here I have a halogen. The NO2 is a strong electron withdrawing group. And then the NH2 right here, it's the nucleophile. So as the reaction goes, the bromine is replaced, and then we get the NH2 instead. For the second one, it's a reduction reaction, and then here we see selectivity. So it could be either the ketone group that's reduced, the ring that's reduced, or the double bond here that's reduced. So then we have the hydrogen and palladium. So palladium acts as a catalyst. And then here, the easiest one to reduce is the ketone group. So as we see, ketone group is gone, and then the structure is as it was. For number C, it's an oxidation reaction. And then here for the substituents, I have the 2-methyl, which have benzylic hydrogens. And then I have this part of substituent here, which I'm not exactly sure what its name is, what it's called, yeah. So yeah, so here the left side, I'm sorry, and then we have here potassium permanganate in water. So potassium permanganate is dissolved in water, and then he acts as a catalyst to not as a catalyst, it increases the rate of the reaction. So right here, this side is the side that's oxidized because there's benzylic hydrogens, and then they allow the oxidation to happen. So here we get 2 carboxylic groups on the side. COOH, COOH, and then this side, as it doesn't have benzylic hydrogens, because this center carbon right here is connected to 4 other carbons, so oxidation does not take place here. For number D, it's a Friedel-Crafts acylation reaction. Here we see the anhydrous aluminum chloride. This is a big indicator that it's a Friedel-Crafts acylation. And then here the chlorine will be added, just the organic part of the molecule. So, and we know that bromine is an ortho-para-director. Same thing with tributyl. It's an ortho-para-director. So here, the butanone without the chloride moves to the ortho location. And as you see, this is how it goes. For question number E, it says explain why a cell group like that found in acetophenone is a meta-director resonance forms in your discussion. So here the double bond breaks, and then here the double bond breaks, and then we get the electrons up here to the oxygen, so we see the negative charge. And then here the double bond is broken again. Positive charges move to this part, double bond is broken again, and then these are like all the possibilities that we can get. So we cannot get there's no more variation that can happen. So yeah, these are all the forms we get. And the reason it happened here, because so the double bond is broken at the carbon with the sp2 hybridization. So it happens right here. And then for number F, it says propose a synthesis for this structure to become this structure. So we added the tin and the hydrochloric acid. We formed tin chloride. It's a strong reducing agent, absorbs the oxygen, and that's what we need to do here to overcome this and then have the NH2. All right, so I'll go over the 5 questions. So the first question was, what is the difference between the Friedel-Crafts alkylation and acylation? And I said that the alkylation reaction adds a simple carbon chain to the benzene ring, while acylation adds an acyl group, creating a ketone or an aldehyde, which happened right here, and then a ketone group was added. For my second question, it's related to question C. It says, why are the 2 methyl groups on the right oxidized and not the left part of the structure, this part? So as I mentioned before, the 2 methyls, they have benzylic hydrogens, which allow oxidation, while on the left side, there is no benzylic hydrogen, as the carbon atom is bonded to 3 other carbon atoms. Question number 3, it's related to question D, which is this one. It says, why did the butanone go to the ortho position of the bromine and not the pair position? So as we mentioned before, the bromine and the tert-butyl, they're both ortho pair directors. So we know it could go here, it can go here, it can go here, it can go here, and it can go here. So we know for the tert-butyl it cannot be in the ortho position because it's a very bulky substituent. So we cannot have 2 bulky substituents right next to each other. So that's why it goes right next to the bromine at the ortho position, as we see right here. And then question number 4, it's related to question F on the assignment, and it says, why didn't we use H2, palladium, and carbon as a reducing agent like we used in question B? Because it's the same concept, it's a reducing agent. And then we can't do that because if we would have done that, then the double bond would have been reduced as well, giving us a different product than what we want. So we want this product, the NH2. So if you would have used the palladium, double bond would have been broken and we would get a different product. And then for question 5, it's also related to question F. It asks, why did we use the tin chloride as a reducing agent? As I said before, it's solvent organic compounds. It's a very strong reducing agent and it absorbs the oxygen, which we need in order to get our product. And that's what happens. Thank you.